All right. Good day, class. Today we're gonna start going into the real physics little by little. Okay. And today we'll be discussing vectors and scalars, vector quantities and scalar quantities. Basically, vector quantities more in details. It's very important that you understand what vectors are because we'll be using them in the later part of this course, talking about Newton's laws and anything that has to do with vectors, forces, and things like that. Okay, so Bismillah. So I'm going to start by defining vectors and scalars. Okay, so in physics, if you remember the first lecture, we talked about physical quantities, and we said physical quantities can be divided into two major groups, or possibly three if you like. We have the fundamental or basic quantities, those that cannot be further decomposed or broken down into sub-quantities. Then we had the derived quantities. They were derived from a combination, a multiple of one or combination of two in terms of multiplication or division. Two or more of the fundamental give us the derived. And then we have what we call the supplementary quantities. Okay, the supplementary quantities, the one called the plane angle and solid angle, which was like the angular displacement and things like that. We'll go into details of this when we talk about the curvilinear or curved motion. Okay, now we want to divide these same physical quantities into some other groups based on some other characteristics. So we're not talking about how they were, if they are derived from others. We want to define physical quantities based on some other characteristics. So the same physical quantities that we have here, that were previously defined like this, are going to be divided into two groups, vectors and scalars. Yes. Now, there are some physical quantities that when you define them by only their magnitude, the number that represent them, okay, the number or set of numbers and the unit, they are okay. Okay? So these are the scalars. So we say physical quantities that require only their magnitude for their complete description and representation are called scalars. These are called scalar quantities or scalars. Are called scalar quantities or scalars, just scalars. So a scalar quantity does not need direction, just magnitude, like mass. I have a mass of maybe 90 kilograms, 90 kg. Just that number is called the magnitude. Just that magnitude is enough to define mass. So mass is a scalar. Time, I walked for 10 seconds. So seconds, 10 seconds, this quantity time is a scalar. I don't need to tell you where I walked to for you to understand that time. So only the magnitude is enough to define them. But there are some other quantities, okay? There are some other physical quantities that require both magnitude and direction. Magnitude and direction for their complete description and representation. So there are some quantities that if you have not attributed direction to them, we cannot fully comprehend them by their magnitude alone. Okay? We must also attach a direction to them. So those quantities are vector quantities. And we have seen some of them before, like displacement. Remember, displacement is distance moved in a specified direction. Distance moved with a given direction. You have to prescribe a direction for that distance. Okay? So if I say I traveled 2 meters north. So this is displacement. But distance, say I traveled only 2 meters. This is distance. So this is a scalar. Only the magnitude can tell us distance. But displacement is a vector because I need a direction. So there are lots and lots of examples of vectors and scalars. I'm going to give you that. Okay? So simple put, or put in a simple way, people usually say vector quantities are those physical quantities that have both magnitude and direction, while scalar quantities are those physical quantities that have only magnitude. So I'm going to give some examples here of vectors and scalars. And I'm going to tell you why these are vectors and why these are scalars. Now we know distance is a scalar. We know displacement is a vector. Okay? We know mass is a scalar, but weight is a vector. Because weight is the pull that gravity has on you towards the center of the earth. The earth pulls on you towards the, so there's a direction. That is why when I jump up, I will come down, because the weight pulls me down in the direction down. So weight has direction. Okay? Weight has direction going down to the center of the earth. So weight is a vector. Okay? Force, which is a generalization of weight, is a vector. Okay? Because it is push or pull. So it has a direction. You're pulling something, you're pushing something, you exert a force on something. Okay? Another kind of force is tension. Vector. Okay? Distance, area, scalar, volume, scalar. 2 centimeter cube of water. I don't have to tell you any direction to understand what 2 centimeter cube of water means. Okay? Those are all scalars. Okay? Then we have density. Combination of scalars. Mass over volume. Density is also a scalar. Pressure is a scalar. Even if it has force in it, it's a scalar because the pressure at the gas or point of a particle is in several directions at the same time. All directions at the same time. No precise direction. So pressure is a scalar. Okay? So I'm going to mention more scalars. We have work, energy, power, speed. And when we say distance, all forms of distance, length, width, height, altitude, depth, these are all scalars. They all fall under distance. So speed, okay, work, energy, power, speed, these are all examples of scalar quantities. Is that okay? Now here for vectors, we have tension, okay? We have moment, momentum, impulse, velocity, acceleration. These are all vectors. So when you prescribe any of this, we expect that you attribute to it a sense of direction. Acceleration, all the fields, electric field, magnetic field, gravitational field, these all have direction, okay? Then altitude, okay, I mentioned it there, altitude and the distance is also a scale, okay? There are many more examples of scalar. Time, okay, it's a good example. Time is a scalar. Is that okay? Work, energy, power, speed, time, area, volume, density. There are lots and lots of them as you come across different quantities. Okay? Friction is a kind of force, so friction will be a vector because it will have direction. Okay? Opposing motion. So we're going to see many more vectors as we go along. So when I say vector, when I mention vector, don't think I'm talking about only force, or only weight, or only displacement. It can be any of these. Any of these can fall into the family of vectors. Okay? So this is an example of vectors or vector quantities, an example of scalars or scalar quantities. Now let's go to business. Let's go to business. We'll go to representation of vectors. Representation of vectors. How do we represent vectors? Yes, so zini zene ha Now, we want to see representation of vectors. Vectors are represented by an arrowhead, okay, that has a length that is equal to the magnitude, okay? The length represents the magnitude. So the longer the length, the larger the magnitude. This is called the tail vector or initial point. And the head of the arrow is called, okay, the head vector or terminal point, terminal or end point. Okay? Okay? So if I have 15 meters to the north as a displacement, or to the east, sorry, this is east, 15 meters to the east. If I have a smaller vector, I cannot call that 20. So that will be about 10 meters east, okay? So 10 meters east will have a smaller line, a smaller length magnitude than 15 meters east, okay? So that is how we represent vectors. So there are different ways of showing the direction of vectors, okay? And I want you to listen carefully because in some texts, they use different notations and they confuse you and you don't know how to actually put that vector in some direction. So I'll give you all the different ways of giving a vector a direction, okay? The first way is to use the axis. The axis. Yes, so we want to see how to represent vectors with direction. Vectors with direction. So we're going to use our Cartesian x and y coordinates, okay? So we have x and y coordinates. So let's say we have a force, which is an example of a vector of 10 newtons, okay? Like this, x, okay, y. So this is positive y, positive x, negative y, okay? If this 10 newtons, so let me put 5 newtons here, and 10 newtons there at an angle I call, say, 30 degrees. Now I want to describe this 5 Newton force, which is an example of a vector. So I'll say there is a force of 5 Newton acting. Some people will say to the right. Yes, that is one way to explain it. It's going to the right. Some people will say 5 Newtons acting along the horizontal. This is partially right because this is also horizontal. Horizontal. So you have to say it is the positive horizontal axis, okay? Because this is also horizontal, okay? So if I have 5 Newton here, I can also call it, let me say 6 Newton, to the horizontal. But I have to tell them what part of the horizontal. So because of this ambiguity in using horizontal, the best thing to do is say 5 Newton acting along the positive x-axis. So this will clear everything, the positive x-axis. So it's acting, so when I want to say 6 Newton, say 6 Newton acting along the negative x-axis, So this is the direction. So when I want to define that vector, I write the magnitude, I give you the direction. I write the magnitude, I give you the direction. So one way of giving direction is to specify the axis. Positive horizontal axis, so maybe I have 8 Newton here. So I'll say 8 Newton is acting along the negative y-axis, okay? Instead of just saying the vertical, because the vertical can be negative or positive. Okay, the negative y-axis. Now, how do I define the 10 Newton? This one has some angle, okay? It has some angle, 30 degrees. So how do I describe the direction of the 10 Newton force, okay? Okay. The same way we did before, using the axis. So that's the first method, using the Cartesian axis. We are going to see another method very soon. Okay, that is commonly used. So now I can say this is 10 Newton at 30 degrees. Don't say to the horizontal, because it can be here and it's still horizontal. So say to the positive x-axis, okay? Or I want to use the y-axis. So this is 90 minus 30, this is 60 degrees. I can still specify that direction as 10 Newton at 60 degrees to the, instead of saying vertical, which is a little bit ambiguous, say positive y-axis. Okay, so I have a choice of how to define the direction of 10 meters. I can use x-axis, I can use y-axis. Any axis you use, you are correct, so long as you have defined the location or position or the direction of that particular vector with respect to some point or origin. Okay, now let us see the other ways of defining these vectors, the directions of these vectors. There are other ways. We use the cardinal points. The cardinal points that we know, north, east, west, south, like I used in that example. So I'm going to take this same example that we did before now, this same example, but now I want to use cardinal points. So I will say 5 Newton is acting east, 8 Newton is acting south. Okay, let me define those cardinal points first. So this is north, up, down is south, right is east, and left is west. Okay? So 8 Newton is south, 5 Newton is east, 6 Newton is west. Okay? Okay? You can say 6 Newton to the left. Negative y-axis or left is still correct. Some people use that. It's still correct. So except they have specified a particular direction in the result of the answer they want, you have a choice to choose the direction and describe it the way you want. Now, how do I describe the 10 Newton force using the cardinal points? Hey, I have 2 angles. I can still use those 2 angles. So it will be 10 Newton acting 30 degrees north of east. So it means you start from east, move 30 degrees towards the north of east. Move 30 degrees towards the north of east. That's where the 10 Newton is. Now, if I want to use the 60 degrees, I will say 10 Newton acting 60 degrees east of north. So it means I start from north, move 60 degrees towards the east of north. Okay? So 10 degrees north of 30 degrees north of east, or 60 degrees east of north. Okay? That is how we use those and they have symbols. North of east. If they want to make a problem difficult for you, some professor want you to fail, okay, they will tell you, instead of saying a force is acting 10 degrees, 10 Newtons at 30 degrees north of east, they will tell you a force acts at this angle. This is the symbol of north of east. And this is the symbol of east of north. Don't get them mixed. This is not east of north. This is north of east in symbol. It means you start from the east, you move 30 degrees towards the north. Okay? That is why it is what north of east. Okay? And then it's for the east of north, you start from north, you move 60 degrees towards the east of north. Is that okay? So this is the symbol for east of north. This is the symbol for north of east. So don't get this confused. And some people, they confuse northeast or northwest. When they tell you northeast or northwest, they will not give you any angle. Because northeast, when you have just say northeast in a problem, it means directly between north and east, 45 degrees. So they will not give you any angle. When they say a force acts northeast, a force of 15 Newton acts northeast, it means it acts directly between north and east. Directly between north and east. Now I'll give more examples to understand these directional problems. Okay? Okay. Now come here. Okay. So I give you a velocity of 18 kilometers per hour in this direction, say 75 degrees. And I say, tell me the direction of this velocity. So you say it is 18 kilometers per hour. So if you like, you say acting at, so we're going to give different directions for this. 75 degrees to the negative x-axis, negative y-axis, sorry. 75 degrees to the negative y-axis because the positive y will be here. Positive x will be here. Negative x will be here. Negative. So it's 75 degrees to the negative y-axis. Or I can say 90 minus 75, okay, 15 degrees, okay. So it will be 15 degrees to the negative x-axis. This is another way to define the direction. Or I say 75 degrees, 75 degrees, this is north, east, west, south. So I say 75 degrees west of south. So it means I start from south, move 75 degrees towards the west of south, okay? Which I can describe as from south, I measure 75 degrees west. So these two are the same. 75 degrees west of south means start from south, measure 75 degrees towards the west. Or I can say 15 degrees south of west. So it means I start from west, I move 15 degrees towards the south of west. So these are 4 different ways that I can represent the direction of this single vector, which is a velocity in this case. Is that okay? So you have the choice to choose whichever one you want, except it is otherwise specified. What if I want to say to the positive x-axis? Yes, I can get the direction of this to the positive x-axis. All I need to do is add 180 degrees to 15. So this will be 18 kilometer per hour velocity at an angle of another direction now, 180 plus 15 degrees to the positive x-axis. Very many textbooks use the angle to the positive x-axis. So not just to the x-axis, the positive x-axis. So when I say horizontal, sometimes most textbooks, they mean the positive horizontal, the positive x-axis. So when you hear horizontal, find the direction to the horizontal. Wherever you are, whichever quadrant you are, this is the first quadrant, the second quadrant, the third quadrant, the fourth quadrant. In the first quadrant, this is the positive x-axis angle. The second quadrant, you take it to the third quadrant. You have to keep going. If you are here, you have to measure clockwise like this. Okay? Okay, you measure clockwise like that, or counterclockwise from the positive x-axis to the vector you want to see the angle to the positive x-axis. So in this case, it's going to be 195 degrees to the positive x-axis. Okay? So be careful. You can always take any direction, understand how to use these directions and how to choose these directions. So if I say represent a displacement of 10 meters northwest, a displacement of 10 meters northwest. So as northwest, this is north, this is west. Northwest means there is no angle. It's just going to be 45 degrees. So this is a displacement of 10 meters northwest. I always have to put my arrow, don't forget. The arrow tells you the direction. Northwest, it could be southwest, 45 degrees. It could be southeast, 45 degrees. Okay? So when I say southeast, okay, don't confuse it with this. This is not southwest. This is west of south of west. Okay? This is west of south. Okay? Don't say it is southwest or west south. Okay? Be careful. When it says southwest, they will not give you an angle. It is splitting exactly the west and the south coordinates or the axis. Okay? For the cardinal point. So this is how we represent vectors. This is what we mean by representation of vectors. Now let's move to addition. Addition of vectors. Addition of vectors. Okay? Zini, zene, ha. We are going there. We are going to the promised land. So then we're going to go to the promised land. We'll see the promised land of Canaan, of vectors. We'll get to that promised land. You discover that you will see a lot of interesting things and interesting physics happening here. Alrighty. Now let's go to addition of vectors. Addition of vectors. So unlike scalars, which can be added by a mere algebraic summation, we need to consider the direction of vectors before we can sum them up. So what do I mean by this statement? If I say I have 10 cm cube of water volume, I have 7 cm cube of water and 3 cm cube of water, I say what is the total volume of water I have? 10 cm cube, I add 7, it's just volume. So volume is a scalar. So mere algebraic summation means add it the way you add in elementary school. 10 plus 7 plus 3, 20 centimeter cube of water. But if I tell you that you have 10 Newton force and you have 2 Newton force, I say, what is the total force? You are not allowed to tell me 10 plus 2, 12 Newton. You are most likely wrong. Why? Because I have not told you the directions of these forces before you can add them. So, by the time you are giving vectors, forces, velocities, displacement, any vector at all, momentum, okay, and I say add them up. The question you ask me is, what is their direction? Be it acceleration, whatever. When you have the direction, then you can add. Because the sum of vectors depends on their direction, okay? And when we sum up vectors, we get a unique answer we call the net vector or the resultant vector. So I will define for you what the net vector is or the resultant vector. And after that, I will tell you how to sum vectors. How to sum vectors. Yes, so it's getting interesting. It's getting interesting. We are going to the promised land. Let me know when you get there. Let me know when you are there. And feel free to ask questions if there is any particular concept or any particular thing you do not understand yet. Yes, so now I want to talk about the net vector. So I said when we add vectors, we get what we call the net vector or resultant vector. So you can call it net or resultant. Net or resultant. So if I say resultant vector means net vector, it means the total vector. Okay? I can also call it total. Okay? Or the sum. You can call it any of those. So we say the resultant vector is that single vector. It is one vector, okay? Is that single vector which acting alone will have the same effect. Will have the same effect as two or more vectors combined together in magnitude and direction. Yes, so this is how we define the net vector, the resultant vector. It is a single vector which acting alone will have the same effect as two or more vectors combined together in magnitude and direction. Now, I said I am defining resultant vector. I am not defining resultant force. Resultant force is just an example of a vector, okay? I'm defining the whole family of vectors, the resultant vector. So if somebody asks me, what is a resultant force? I will just replace everywhere vector is here with a force, okay? The resultant force is that single force which acting alone will have the same effect as two or more forces combined together in magnitude direction. Resultant displacement, replace everywhere here with displacement. Resultant velocity, replace everywhere here with velocity. Resultant acceleration, replace so this vector can be any vector. So I'm defining a general definition. So whether it's a force, whether it's acceleration, whether it's velocity, whether it's momentum, anything it is, any vector at all has the resultant defined like this. Yes, on the way to the promised land. Yes, so now this is the resultant vector. I will tell you what it means now in real life. Now we want to see addition of vectors, how we add vectors. So for addition of vectors, we're going to take cases. Case 1, vectors acting in the same direction. That's the first case, the simplest case. So I have a body here. I have a force, I take a force as an example of my vector now, of 10 Newton, another force of 15 Newton, both acting towards the east. And I say, what is the net force? Okay, or the resultant force. So I call the resultant force, I call Fr, or net force, you say Fn, you can define it as you want, this is where I add 10 plus 15, 25 Newton, that's the magnitude I put east for the direction. So it has to be magnitude and direction all the time. So this is the only way I can add vectors when they are in the same direction. That is when I can add them like the way I add scalars, by mere algebraic summation. That is case 1. Vectors in the same direction. When they want to confuse you, instead of telling you that these vectors are in the same direction, I can tell you that the 10 Newton force and the 15 Newton force are acting at an angle of 0 degrees between them. An angle of 0 degrees means they are along the same line. Okay, it means they are in the same direction. So don't get confused. Another way to confuse you for vectors in the same direction, they will say they are parallel to each other. So I have 15 Newton and 10 Newton acting parallel to each other. So they are parallel to each other means they are in the same direction. And it doesn't have to be east. They could be like northeast, 10 Newton and 15 Newton. They will still add up to 25 in that same direction. It is just the direction that will change, okay? So when they are parallel, it means they are 0 degrees to each other. It means they are acting in the same direction. So this is the simplest case. So let's go to case number 2. Case number 2. Oh yes. Case number 2. Yes. We are going there. Hey, the land of 2 member. Yes, sir. 1 plus n all over 2 member. You know, I was teaching a class one day, and then one of the students said, "You are too fast, I can't understand." And I was like, "You don't understand?" And there was a lizard at the top of the roof in the class, and the lizard was nodding his head to me because the lizard could understand. You know, if the lizard can understand, nodding the head, why can't you understand? Huh? You should understand. Okay, now tell me when you don't get anything clear, and we go back and explain to you so you can understand and nod your head like the Agama lizard. Agama lizard. Yes, so case number 2, addition of vectors. Now we have vectors acting in opposite directions. So how do I get, so the same block now, so I have 8 Newton towards the west and 3 Newton towards the east. I say, what is the net force? Okay, the net force here, or resultant force, or net force, anyone, is the subtraction of the small one from the large one. So it's like a baby and an adult dragging this box. So the adult is going to, you know, defeat the baby and take, so the resultant is going to be in the direction of the larger force. So it's 8 minus 3, 5 Newton west. Or you can say negative x-axis. The same day you can say positive x-axis or east. It's the same. It's your choice of direction. Okay. 5 Newton west. So when I say vectors are acting in opposite direction, you see now what I mean when I told you that when you are giving 2 forces, you can't just tell me the net force or the total force, except you already know the direction. So if 8 and 3 were acting in the same direction, it would have been 8 plus 3, 11 newtons towards that direction. But now in opposite direction, it is 5, so the direction affects the magnitude of the net force. It affects the magnitude of the net force. Yes, so now I'm going to, before I go to case number 3, I want us to use the result we have gotten for the net force of case 1 and case 2 to understand our definition of the net vector or the resultant vector. I said the net vector is that single vector, so it is one vector, as you can see in this case, 25 Newton east. In that case, it was 5 Newton west, which acting alone will have the same effect as 2 or more vectors combined together. What does that mean? It means instead of combining 10 Newton and 15 Newton, 2 different vectors, I can take this single 25 Newton, one single force, act it on this body towards east. It will have the same effect as these 2 combined together. That is why it is called the resultant or the net. If I come here, the same thing, the resultant is 5 Newton west. So instead of me taking 3 Newton east and then acting 8 Newton west and take the difference, I could take a single 5 Newton west force on the same body. It will have the same effect as these 2 combined together. That is the definition of a net force or resultant force or resultant vector. Okay, in general, vector. This could be velocity, it could be acceleration, but we are just very used to using force, and people think vector is all about forces. No, it's not. It's not. Now let's go to case number 3. Case number 3. Vectors acting orthogonally. Vectors acting orthogonal to each other. Orthogonally means perpendicularly. Perpendicularly means at 90 degrees to each other. So I have a vector here, say 3 newtons, and another vector here, say 4 newtons, and the angle between them is 90 degrees. So when I say what is the net force or net vector here? They are not in the same direction, so I can add. They are not in opposite direction, so I can subtract. Now they are acting in a different way. So the way is simple. When they act perpendicularly, you complete the rectangle and you draw your net vector or net force from the point of intersection of the vectors. If they are in this configuration, we're going to see other configurations very soon. From the point of intersection, I call that my FR, my resultant force. Okay, my resultant force. Then how do I compute my FR? It's a right angle triangle, so the rectangle, we have right angles everywhere. So I can have the right part of that rectangle, which is a triangle like this, half of it, 3 newton this way. This is 4 newton, this is also 4 newton, 3 newton, 3 newton. Okay, this is 4 newton now, this way. Okay, and this is my FR. And this is 90 degrees. So a right angle triangle, we can always use Pythagoras rule to get the third part of the triangle, the hypotenuse in this case. So I say FR square equals 3 square plus 4 square, which is 9 plus 16, which is 25. So my resultant force is just square root of 25, which is 5 newton. That is the magnitude, 5 newton. I have to get the direction. In this case, the direction is going to be an angle. It's not directly east or west, it's at some angle. So once I get that angle, I have also gotten the direction. So how do I get the angle? How do I get the angle? This is where we introduce to you the principle called the SOHCAHTOA in mathematics. The SOHCAHTOA principle of mathematics. The SOHCAHTOA principle of mathematics. So we say when we have a right angle triangle, I'm going to draw very big. It's a right angle triangle. And I call this angle theta. Okay, the line facing the angle are called opposite, or the line joining the angle to the 90 degree line, I call it adjacent, A. And the longest line I call hypotenuse, H. So if I want to get this angle theta, there are different ways. The first one is sine. Sine theta is opposite over hypotenuse. So it means theta is the inverse sine of opposite over hypotenuse, okay? In your calculator, to get theta, after dividing opposite hypotenuse, to get theta, you have to take away this sine by taking the sine inverse of this opposite over hypotenuse, which I say O over H. That would be shift sine in your calculator, okay? Shift sine or second function sine. And then you get your theta. I'm going to use this as an example. Then we have cosine. Cos theta is adjacent divided by hypotenuse. So this is the same theta. I'm just telling you different ways to get it. You can use the sine, depending on what you have. So if I don't have hypotenuse and I want to get theta, it means I cannot use sine or cosine because they both have hypotenuse inside. Okay? Okay? You see, we can use the third one. So theta becomes cos inverse of adjacent over hypotenuse. And then the last one is called the tangent. Tan theta is opposite over adjacent. Okay, so what is theta? Is tan inverse of opposite of adjacent. So if I don't have hypotenuse, I have opposite and adjacent, I can use tan. If I don't have opposite, I have only adjacent and hypotenuse, I will use cosine. If I don't have adjacent, I have only opposite and hypotenuse, I will use sine. I will get the same answer for theta. So it's just your choice, okay? And we're going to see that availability now in this problem. So let me go back to this problem, the case number 3 problem. Okay. I know I was a little bit fast in that. Case number 3. I will review it again a little bit so it's bigger. So it started with 2 forces, 3 Newton and 4 Newton, acting, and as I was asked at 90 degrees to each other, I was asked to get the net force. So we completed this. We call this our resultant force or net force, going in that direction at some angle we don't know, we call theta. So some people will say he's going to share it into 2, like 45, 45. No, it will only be 45, 45 if these 2 sides are the same. So this side is longer than that side. So that angle is definitely not 45 degrees, something else, okay? Okay, now we say this is a right angle triangle here also. So here is 4, It's a rectangle now, this whole thing, 4, 3, here's 3. Then I just work with only that 4, 3, the right hand part, I call the B part. I'm going to shade that. This B part of the rectangle. And that's my FR. So I said this is a right angle triangle, that part. And I said FR square is 3 square plus 4 square. From there we got FR to be square root of 25, which is 5 meters. Now I want to get the direction theta, which is going to be a direction to the positive x-axis, okay? Or you can call it a direction that is north of east. It's your choice, okay? But now let's get it. Now we have opposite and we have adjacent. We also get 5 Newton, which is hypotenuse. So we also have hypotenuse. So we have a choice to use any of those three because we have everything. So if I use, for example, tangent, I say tan theta is opposite 4 over adjacent 3, 1.333. So theta is the tan inverse of 1.333. If you press your calculator, that will give you theta as 53.13 degrees. So I now say, maybe I want to use sine. You see, we get something. Sine theta is opposite of hypotenuse, 4 over 5, okay? And then if you take tan inverse of 4 over 5, it's still going to give you 53.13 degrees, okay? Or you say, you want to use cosine, 3 over 5, you take the tan inverse of 3 over 5, it's still going to give you 53.13 degrees. So any of the ones you use, you get the same answer. So we say our net force, Fr, is 5 newtons at an angle of 53.13 degrees to the positive x-axis, which is this, positive x-axis, like this. So this is the resultant at that angle to the positive x-axis. Or you say 53.13 degrees north of east. Or you say start from east, move 53.13 degrees north. Or if you like, you can decide to use the angle to the vertical. Call it alpha. So 90 degrees minus theta will give you 53.13 degrees, 30 minus, subtract it from 90 degrees, okay? 0.13, okay? So this will give us 7, 9 minus 1, 8, okay? 9 minus 3, 6, okay? And then we have 8 minus 5, 3. So 36.87. So I can say 36.87 degrees to the positive y-axis. So I'm using this angle. I'm describing the same thing. Or I said 36.87 degrees east of north. It's your choice. Okay? It's your choice. Just take that choice and use it the way you want. Okay? Okay? Now, that is how we handle vectors that are perpendicular. Please, it is very important you know how to resolve vectors that are perpendicular to each other, okay? I'm going to take another example to make that clearer right now for vectors that are perpendicular to each other. So we see how that works. Okay? Now, I have a lot of forces acting here, okay? So I have 20, let me use meters per second, now velocities, okay? I'm tired of forces. Velocities, okay? I have 20, here I have 6 meters per second, here I have 8 meters per second, okay? So here I have 20 meters per second, okay? And then here I have 6 meters per second, okay? Okay. Then here I have, say, 10 meters per second. Here I have, say, 15 meters per second. Here I have, say, 20 meters per second. And here I have, say, 10 meters per second. So I said, what is the net velocity? Not net force now. What is the resultant velocity? Because I'm discussing velocities here now. Okay. What is the resultant? Find the resultant velocity of this system. Okay. So we go stage by stage. So the first stage is these two are in the same direction. I add them. These are in the same direction. I add them. These are in the same direction. I add them. These are in the same direction. I add them. So this will give me something like this. Single forces in those directions, or single velocities in those directions. 10 plus 15, 25 meters per second. 20 plus 10, 30 meters per second. 8 plus 6, 14 meters per second. 20 plus 6, 26 meters per second. So this diagram and this diagram are the same. So those forces, the 8 forces, 1, 2, 3, 4, 5, 6, 7, has reduced to just 4 by adding those in the same direction algebraically like we did in case 1. Now we go to case 2. We subtract opposite forces. 26 is greater than 14 and 30 is greater than 25. So now it will go back to 2 forces. Okay? It will now go to perpendicular forces that we already know how to solve. Okay? So right now, here in this case, this will be the same diagram now. I will draw it, that same box. Now I have 26 minus 14. That will give me 12 meters per second going that way. 30 minus 25. That will give me 5 meters per second going this way. Now I want the net force. This is exactly like the example we just took, but in a different quadrant. So this becomes like this. So I will make this a little smaller than that of the 12 meters per second, and this is 5 meters per second. I complete the rectangle. My net force will come from the point of intersection, or net velocity, let me call it VR now, resultant velocity. Right angle triangle, right angle triangle, right angle everywhere, okay, 90 degree everywhere. So I can find this angle, or I can find that angle as my direction, my choice, depending on how I want to represent it. So in either case, my VR sequoia is 5 sequoia plus 12 sequoia, 25 plus 144, 169. So my resultant velocity is square root of 169, 13 meters per second. 13 meters per second. Now, how do I get my direction? So I can say tan alpha is opposite. So this will be opposite if I'm using alpha. Opposite is 12, 5, here is 5. Adjacent is 5. So it's 12 over 5, okay? Okay, that will give me 2.4. So alpha will be tan inverse of 12 over 5, okay? And that will give us about 64.7 degrees. You can verify that for me, please, okay? Where's the other way around? The other way around, right? Okay, 67.4 degrees, okay? Okay. So I will say my resultant velocity is 13 meters per second at an angle of 67.4 degrees to the negative y-axis. That is one way to describe it. Or I subtract that from 90, it will give me 20 something, okay? About 22.6 degrees, that's theta. 90 degrees minus 67.4 degrees, about 22.6 degrees. So it will be 22.6 degrees to the negative x-axis. What if to the positive x-axis? So it will be 22.6 here plus 180 degrees to the positive x-axis. Any of those directions will work. Or if I like, I say alpha, my direction is alpha west of south, or theta south of west. Any one at all. So you see, you have a variety of directions to choose from to represent your net vector. Except if the professor has fixed a direction and he wants you to use that, so you have to use that direction alone to get the answer that you want. Alrighty. So the aim of every vector problem, most of it, when we want to resolve forces, is to reduce a complicated problem like this into a perpendicular problem like this. Okay? So the perpendicular problem can be in any quadrant. It could be like this, in this, it could be like that, it could be like this. Anyhow it is, you know how to get the direction as you want and as your, at your own discretion, your choice. You make the choice of the direction. Okay, that is case number 3. Case 1, vectors in the same direction. Case 2, vectors in opposite direction. Case 3, vectors are perpendicular to each other. Oh, talking about. Well, we go to case 4. We have a case 4. Let's see case 4. I'll come here to case 4. Case 4, vectors acting at an acute angle. Acute angle means greater than 0, okay, but less than 90 degrees, okay? So for example, I have 10 meter displacement, and here I have 5 meter displacement at an angle of 60 degrees. So I say, what is the next displacement? Now, they are not in the same direction like case 1. They are not in opposite direction like case 2. And they are not at 90-degree right angle like case 3. They are in a smaller angle we call acute angle. How do I get the net force or the net displacement in this case? Here we use what we call the parallelogram law of vectors, okay? The parallelogram law of vectors. So the parallelogram law of vectors states that if two vectors, okay, acting, let me see, if two vectors can be represented by the adjacent sides of a parallelogram, then the resultant vector, so it could be forces, it could be displacement, the resultant vector is the diagonal of the parallelogram, drawn from the point of intersection of the two vectors in magnitude and direction. So I'm going to explain this. What it means is we can complete this to look like a parallelogram. Once we can complete this so that the two vectors are like the two sides of the parallelogram. So this is 10, this is also 10 meters, this is 5, this is also 5 meters. So once I can complete a parallelogram from the way the vectors are, and then I can get the net vector or the resultant vector as the diagonal of the parallelogram from where the vectors intersect, like this, tail to tail, okay, tail to tail, not here, but here. So this line is my resultant displacement. I'm going to call XR, resultant displacement, okay? So from the point of intersection, the arrow goes that way. That's going to be my net displacement, or my net vector. Now, if I can calculate the magnitude of this line, I will get that. Then I need also a direction I'll call beta, okay? To know the direction of the resultant force. So we're going to use some mathematical things here. I'll just take this part, this down part out. Let me call this angle gamma, okay? So first of all, let me do this. Let me come here. So now we want to solve that problem. So I'll take the bottom part of that, 5 meters, 10 meters, and this was my XR, this was beta, and this was gamma. And don't forget, it was like this. This was 60 degrees, okay? Okay, the other 5 meters was here, and the other 10 meters was here, okay? I want to work with this triangle only, okay? This was gamma, okay? First of all, gamma is 180 degrees minus 60 degrees to give us 120 degrees because base angles of a parallelogram are supplementary. Supplementary means add up to 180 degrees, okay? So base angles of a parallelogram, 60 and gamma will add up to 180. So gamma will be 180 minus 60. But I can't tell what beta is for now. So why am I doing this? I'm constructing a triangle that has 120 degrees here. I'm looking for XR. I know here to be 5 meters. And I know here to be 10 meters. And I'm looking for XR. When we have such situations, we use what we call the cosine rule. We use what we call the cosine rule, or the cosine law of mathematics. So I'll show you what the cosine law is. The cosine law. So the cosine law says if I have a triangle like this of angle A, B, and C, such that the line facing angle A is line A, the line facing angle B is line B, the line facing angle C is line C, I can get A square as B square plus C square minus 2BC cosine the angle facing the line I'm looking for, cosine A. If I'm looking for B, B square is A square plus C square minus 2AC cosine the angle facing the line I'm looking for B. I'm looking for C, C square is A square plus B square minus 2AB cosine C. Okay? There's also this what we call the cosine rule. There's also what we call the sine rule. Okay? The sine rule just says that the sine of an angle over the line is the sine of another angle over the line facing that same angle. So this is the same sine C over sine C. So any of these two can be equal. This equal that, this equal that, or this equal that, as you like. Okay? So we're going to use a combination of the cosine rule and the sine rule to solve this problem. Okay? Now our problem, remember, is like this. We have 10 and 5, 10 meters, 5 meters. I'm looking for XR and I know the angle 120 degrees. I'm done. So it's like the cosine rule. So this is A and the angle facing A 120 degrees and I know B and C. I can get everything from the cosine rule. Okay? Now how do I get my XR? Now using the cosine rule. Okay? So using the cosine rule, I'm going to come here now. Using the cosine rule, XR square, let me just call it X just to be easy. X square is 5 square plus 10 square minus 2 times 5 times 10 cosine 120 degrees. So that was why I was looking for that gamma first, that 120 degrees first. Okay. So 5 square is 25, 10 square is 100, 2 times 5 times 10 is 100, cosine 120 degrees is minus 0.5. So 25 plus 100, 175, okay. 125 minus 100 times 0.5 is 50, so minus minus becomes plus. 175 newtons. Oh, sorry, I'm working in meters. So x is square root of 175, 13.2 meters. So that is my net displacement, 13.2 meters. I've gotten the magnitude. To get the direction, now I have to come back here and I have to use sine rule. So I know this, I'm looking for the direction of this, okay? The direction here, which I call beta. So I'll say sine beta over the line facing beta, 5, equals sine 120 degrees over x. I just got x, 13.2. I don't know if you're getting this clear. Okay, so I use cosine rule to get my magnitude. Now I'm using sine rule to get my direction. Okay? This is how you attack this case once it is at an acute angle. We see it is the same case for an obtuse angle. Okay? So this will give us sine beta over 5, sine 120, 0.866 over 13.2. So sine beta is 5 times 0.866 over 13.2, which will give us 4.33 over 13.2, which will give us about 0.33, I guess. You can cross-check that to verify for me. Right? Okay, good. So beta is the sine inverse of 0.33, which will give us about 19.3 degrees. Verify that also. I think that should be correct, 19.3 degrees. Now, my displacement, my net displacement is 13.2 meters at an angle of 19.3 degrees to the positive x-axis, if you like, or positive horizontal, or 19.3 degrees north of east. Or if you like, you can decide to calculate 90 minus that to get the angle west, east of north. Your choice, okay? Your choice. Now let me show you another way to get this without having to calculate the 120 degrees angle here, gamma. So I'll come back here. So I will draw the problem again, okay? I will draw the problem again. So remember the problem was like this. 5 meters, 60 degrees, 10 meters. Then we completed this parallelogram. Parallelogram means sides are parallel, opposite sides are parallel, okay? So here is 5, here is also 5, here is 10, here is also 10. So my net force was the line from the intersection of the vectors, which I call x, okay, net displacement. So instead of looking for this angle I call gamma to use the cosine rule, we can also use the cosine rule by using the angle between the two forces or vectors. So I could say x squared directly with cosine rule is 10 squared plus 5 squared. Instead of minus, now I'll say plus. It was initially minus, but now I'll use plus 2 times 5 times 10. I will say cosine 60 degrees, where 60 degrees is the angle between them. So if I do like this, I'll get exactly the same answer. This is 125 plus 50, 175, and x is just square root of 175, which will give us the same 13.2 meters, okay? Meters, not meters. Okay, yes. So you can either use the angle between them or use the angle here and use a minus here, your choice. You get the same result. But the direction is the same, you use the sine rule. So this is also the cosine rule, but using a different angle, okay? Beware of that, okay? Don't use a plus and use 120. And don't use a minus and use 60. Then you get the wrong answer. You get it wrong. You get the wrong result. Okay? Now, what if they want to confuse us? They give us an obtuse angle instead. An obtuse angle means it is greater than 90 degrees, but less than 180 degrees. Something like this. So I have two forces, say 8 newtons and 4 newtons, at an angle of, say, 110 degrees. I say, what is the net force? It's the same. Draw the parallelogram. Some people will draw parallelogram like this because of what they are used to. This is not parallelogram. This has become trapezium. This is so parallelogram has to be parallel. So parallelogram is this, okay? This is the correct parallelogram. These sides, okay, and these sides must be the same. You see that now? Line is going this way, sorry. So this side's like that. So this is 4 meters or 4 newtons. This is 8 newtons. So also the net force will be from the point of intersection. I call Fr or Fn. The same thing. I can get this angle theta and use my cosine rule. Fr square is 8 square plus 4 square minus 2 times 8 times 4 cos theta. Or I use 110 degrees and use a plus. 8 square plus 4 square plus 2 times 8 times 4 cos 110 degrees. I will get the same result. So whether it's obtuse, whether it's acute, the parallelogram law of vectors work. In fact, the beautiful thing about parallelogram law of vectors is when we discuss this, remember when vectors are perpendicular to each other? When we had 4 newtons and 3 newtons, and we said we draw what we were doing was the parallelogram law. Okay? Complete this to be a parallelogram. A rectangle is a parallelogram because the opposite sides are parallel. A square is a parallelogram. Okay? It doesn't have to be like that, okay? So this rectangle now, which is a parallelogram, I say I join the line from the point of intersection of both vectors. Be careful. Some people will do like this and say the net force is like this. Yes, you will get the right answer, but you will get the wrong angle. This one is wrong. And by the time we come to vector geometry, at the end of the class, we talk a little bit about vector geometry. You understand how the angles and arrows work, and this whole concept will become very more interesting for you. So when you have vectors perpendicular, this is the right net vector, not this one. This is the correct one, not that one. So let's see, I said this is also parallelogram law. How? Yes. Now I'm going to use cosine rule. Pythagoras theorem, you see, is actually cosine rule. How? This is 3, this is 4. I'm looking for, let me call this R. So R square, the line, the angle facing R is 90 degrees. You see that? So it's 3 square plus 4 square minus 3 times 4 cosine 90 degrees. You discover that cos 90 degrees is 0. So 0 will kill this whole term. So it just becomes 3 square plus 4 square, which is what you call the Pythagoras rule. So what we were actually doing there was still the parallelogram theory, the parallelogram law. Okay? Good. Now we have seen different cases. In fact, when we go along, you discover at the end of this course, you will see one problem. We're going to teach you, you will have more than 5 different methods to solve one problem. It becomes your choice. So we've just been seeing one method so far. Okay, there is a very ultimate method we're going to go into now. It has something to do with a property of vectors called decomposition of vectors or resolution of vectors. Once you understand resolution of vectors, everything, you see that this problem, you don't even need to use parallelogram law. You can use that decomposition of vectors or resolution of vector method to get the same result. And I'm going to explain that right now. I will explain resolution of vectors though, by telling you a story. Okay? A story for resolution of vectors. So resolution or decomposition of vectors. When I was small, I had a friend, his name was Junior. The parents bought him a toy. So sometimes Junior, he has this toy car, okay, that the parents bought him. A very beautiful and pretty looking toy car. So sometimes Junior is playing with this toy car like that, okay. So you see this toy car. So while Junior is playing with this toy car, sometimes you will see that Junior, okay, will push this toy car along the horizontal, okay, with a force, push it. Okay, sometimes Junior will raise the car up. At the time he got tired, he attached a rope to the car and started pulling the car this way on the ground. 3 questions. When Junior was pulling the car to the right, where would the car go? To the right, right? When Junior carried the car up, where would the car go? Up. When Junior pulled the car with the rope, where will the car go? No, the car will not follow the rope. So this is what the decomposition of vectors will teach us. Is that okay? Okay, I'm going to take a practical example in the class for us to see what's going to happen right now. So I'll grab this table, okay, and I want you to watch with me. Okay, it's okay, I'll bring it forward where everyone can see. Okay, that hurts. Okay, now I have this table. Let me bring it here. It's quite heavy. Let's say I want to raise this table up with a vertical force. The table goes up. If I push with a horizontal force that is flat, the table goes like that. But if I say carry this table, sometimes I incline my hand to the table at some angle, okay? And I carry the table. You see, the table is not coming towards my hand is inclined. You will discover that the table is moving towards this way. At the same time, part of the table is raised up. Part of the table is raised up, and the table is moving at the same time. So 2 things are happening. So what happens is, when a force acts at some angle, okay, when a force acts at some angle, so let's use that table. I call this F up, I call this F right, and I call this F at some angle theta. So when I have this F at some angle theta, this object will not be going in that direction. What happens is, when you act a force directly up, all the force is directly up. When you act the force directly horizontal, all the force is directly horizontal. When you act the force in between the horizontal and the vertical, then some of the force will be in the vertical. That was what was raising the table up. And some of the force will be in the horizontal. That was what was pushing the table at the same time. So the axis will share the force. Some of the horizontal will get the force, some vertical will get the force. The part of the force that is acting along the horizontal is what we call the horizontal component of the force. And the part of the force in the vertical is what we call the vertical component of the force. Okay? We're going to see some magic that are happening here. Let me turn this. You see some magic that is happening here. I'll give an example now, okay? Let's take this example. I have the x and y axis, and I have a force of 10 newtons at an angle of 30 degrees. So I know that this force has a horizontal component and a vertical component. So what is the horizontal component? Once you know the angle to the component you are looking for, the simplest way is, instead of doing the SOHCAHTOA again, okay, the simplest way is doing this. So when I said SOHCAHTOA the last time I did explain, it's like this. SOHCAHTOA is a short form of sine, opposite of hypotenuse, cosine, adjacent of hypotenuse, tangent, opposite of adjacent. That's what we call SOHCAHTOA. So it's just a simple form for you to remember. Sorry, the last time when I explained, I didn't show I just mentioned it at the show. So we can use SOHCAHTOA here, but there is no need. Let me tell you the short form. Once you know the angle to the axis, this is the x-axis, this is the y-axis. I want to get the x and y component, the horizontal and vertical component of this. Which axis has the 30 degrees? The x or y? The x. So the x, the one that has the axis, will take a cosine. So my x component I call fx, which is the horizontal component horizontal or x component of the force, it will be 10 times cosine of the angle, cos 30 degrees. 10 times 0.866, that gives us 8.7 newtons. So out of 10 newtons, 8.7 newtons is acting along the horizontal. Now let's get the vertical component, Fy, which is called the vertical or y component of the force. Now, is 30 degrees the angle between the vertical and the force? No, then I will use sine. That's the short form. So my Fy will be 10 times sine of the same angle, 30 degrees, which is 10 times 0.5, which will give me 5 newton. Listen, I used cosine for the x-axis because the x-axis had the angle. I used sine for the y-axis because the y-axis did not have the angle. What am I trying to say? If the problem, the 30 degrees was here and not here, then I will use cosine for my vertical component and use sine for my horizontal component. So be careful. It is not that always the vertical is sine and the horizontal is cosine. No, it depends on the axis that has the angle. In fact, by the time I explain to you, you can use any angle you like. So this problem had 30 degrees here, okay? Okay? You can use cosine for both axes. You can use sine for both axes, depending on the angle you have. Let me explain what that means. Look at this. Look at this, guys. We are going to the promised land as I promised. Look at this. The same problem. Y-axis, x-axis, 10 newtons, 30 degrees. Now, horizontal component fx, I say is 10 cosine 30 degrees. I use cosine because the horizontal has the angle. Fy, I say 10 sine 30 degrees. Okay? This just gave us 8.7 newtons. And this gave us 5 newtons. I don't want to use 30. I know this is 90 degrees, this will be 60 degrees. I want to use 60. If I'm using 60 degrees, my Fy will now have a cosine because 60 degrees is the angle to the y, okay? It will now be 10 cosine 60 degrees. You will discover that cosine 60 and sine 30, you will get the same 5 newtons. And Fx, I want to use 60 degrees for x, it will be 10 sine 60. I'm using sine because 60 is not the angle between the first and the x-axis. It will still give me 8.7 newton. So any angle you use, you get the same answer. So I can decide to use cosine for both axes. I can say my Fx is 10 cos 30 degrees and my Fy is 10 cos 60 degrees. Because I know those two angles. I'm right. Or I can decide to use sine. My Fx is 10 sine 60 degrees and my Fy is 10 sine 30 degrees. I'll get the same answer. So it is your choice to choose whichever angle you want to use. Now let's look at this. I said when we have a force here, it is shared between the x and y axis. Okay? The x component was 8.7 newtons. The y component was 5 newtons. Which component had the bigger part of the force? The x. Why? Can you tell me why? Do you know why? The x component had the bigger force because the force is closer to the x. You see, 30 degrees is smaller than 60. So it's closer here. So the more the force goes here, the more of the force will be in the x and less of the force. So if the 10 was 30 degrees here to the y and 60 degrees to the x, so you discover that more of the 10 newton will now be to the y and less of the 10 newton will be to the x. So the closer the force is to an axis, the more of the component or the force that component will get from that force. That's one point. Second point. I said the axis will share the force. I'm going to make 3 points here. Please follow me. These 3 points are very important. The first point I just made is the closer the angle is to an axis, the more of the force that component will get. Or vector, whatever vector. Now, the second point is, I said they share the force. When you share 10 newton between x and y, x got 8.7, y got 5. When you sum up 8.7 and 5, it's bigger than 10. We're supposed to expect a proportion of 6, 4, 5, 5, 3, 7, 8, 2, something like that. So why is it that when you share the force, it gets bigger? It doesn't get bigger. It's because you are adding wrongly. You are adding the forces wrong. Don't forget these are vectors. So, this brings me to the third point. Listen attentively. Listen attentively. If I have a force of 10 Newton acting at an angle of 30 degrees to the horizontal or positive, this is equivalent to, once I get the x and y component, this is 5.8.7 newtons, which is 10 cos 30 degrees, and this is 5 newton, which is 10 sin 30 degrees. These two are the same. In fact, this is the effective force. This is what is actually happening, not this. So when you see a force, you resolve it to its component. Okay? This is the third point I want to tell you. So this diagram, this is like artificial. This is not really happening. What is really happening is when you resolve the components, when you get the x and the y component of this force, which is this and this, then the force disappears. You see the force is no longer there. We take it away. What we need is the component. So when we see a problem where a force is in between an axis, the first thing you do, get the x and y component, then you throw away that force. Use the component. That is the effective force of what is happening. Okay? Whether it's velocity, displacement, anything in between an angle. And we're going to take some examples like that. Now, back to the second question. Why do we have 8.7 and 5? When we sum them up, they are bigger than 10. Like I said, you are summing wrongly. Don't forget, when we sum like vectors. So we have to complete this like a parallelogram and draw our net FR. So FR will be 5 square plus 8.7 square. When you take the square root of that, it will give you 10. This is the right way to sum. So when you sum it the right way like vectors, that is when you get back the 10. So it is a decomposition. The vector is resolved or decomposed into the x and y components like this, and then you can recompose. You compose back from the x and y component to get back the single force that decomposed into that. So it is like killing a vector and resurrecting the vector. You can kill the vector into component, you can resurrect the vector back from its components. So I'm going to take some examples here. And I want you to listen very attentively to these examples. Yes, sir. Yes, sir. Yes, sir. Yes, sir. I have a force, an example, of 15 Newton acting along the vertical like this and this. So I ask the question, what is the effective vertical force? The effective vertical force is just 15 newtons towards the positive y-axis. What is the effective horizontal force? Effective horizontal force is 0 because the vector is straight along the vertical. It has no business with horizontal. What is the net force? The net force is the same as 15 Newton to the positive y-axis because it's the only force active there. Is that okay? The same thing if I put like this, a force of 10 Newton acting along the horizontal. What is the effective vertical force? 0. What is the effective horizontal force? 10. What is the effective net force, the total for 10 towards the east? Now, let's visit this again. Now I have a force of 20 Newton at an angle of 30 degrees. So I say, what is the effective horizontal force? So the effective horizontal force is just 20 cosine 30 degrees, 17.32 newtons. What is the effective vertical force? That's the vertical component. Okay, effective vertical force is just 20 sine 30 degrees, which is 10 newtons. So if you like, you can say, no, I want to use 60 degrees. So the vertical will be 20 cos 60, which will give you the same answer. And the horizontal will be 20 sine 60, which will give you the same answer. So anyone you like, you can use. Okay? You get the same answer. What is the net force? The net force is just the 20. Because that's the net force of those two when you recompose them back after decomposition. Okay? Okay? Okay, okay. Now I want to tell you, if you understand how to resolve forces, then you know half of vectors. 50% of vectors is gone. 50%, I'm not kidding, I'm not joking at all. I want to revisit the parallelogram law problem, and I want to solve it using the vector resolution of vectors. Oh, you will see the power of resolution of vectors. The power of resolution of vectors. Right now, remember the problem. It was like this. So instead of using the cosine law, parallelogram law, sine law, instead of all those long stories, see what this is going to do. 10 meters. So I complete this was 60 degrees. I draw imaginary x and y axis here. So this x-axis, y-axis, x-axis. 10 Newton is already along the x-axis. Okay? 5 Newton is in between. So once it's in between, I know it has a vertical and horizontal component. So I get the vertical component 5 sine 60. And the horizontal component is 5 cosine 60. That we add to this that's already in the horizontal. Plus 5 cosine 60. So this results to this. 10 plus 5 cosine 60, and here 5 sine 60. That 5 is gone because I have gotten the x and y component. And this one, 10 is still here. The horizontal component of 5 will add to it. And I just take the vertical component. And those are no other forces there. It has come to 2 perpendicular forces, which I know how to get the resultant. Okay? Okay, so I finished that. That will give me 5 sine 60 degrees, which is 4.33 newtons. And 10 plus 5 cos 60 is 10 plus 2.5, 12.5 newtons. Okay? You see that? Then I get my net force, Fr. So which is 4.33 sequoia plus 12.5 sequoia square root as my Fr. You see this will give you the same 13.2 newtons. But then we use meters as displacement. Sorry, but now I'm using newtons as force. Don't get it confused. You get the same 13.2 you got before. And to get the angle, instead of using cosine sine rule, just simple tangent. Opposite, this is 4.33, adjacent 12.5. So tan theta is opposite 4.33 over adjacent 12.5. If you take the tan inverse of that, you get your theta to still be 19.3 degrees. The same answer exactly, in 2 lines. Because I understand how to resolve vectors. I don't need to draw parallelogram, use cosine rule, find an angle. Now you already know 2 ways to solve one problem. Hey, 2 ways to solve one problem. The aim of resolution of vectors is any number of vectors you have, you can get their x and y components, sum up all the x components, sum up all the y components, it will reduce to something like this. The direction might be different. It might be in this corner sometimes, if the y is positive, x is negative this side sometimes. It can be anyhow, but it must be only 2 forces. 1, 2, 1, 2, 1, 2, 1. Only 2 forces will be left that are perpendicular, and you already know how to resolve such a problem when you have 2 forces that are perpendicular. That is the aim. Another advantage of resolution of vectors is the parallelogram law of vectors cannot sum 3 vectors. For example, if I have 3 forces like this, another force here, another force here, I say find the net force. I cannot use parallelogram law of vectors for the 3 at once. I have to first of all solve these 2 using parallelogram law, get a net force. Now use the net force and use parallelogram law and add it to this one, which is very cumbersome. But if I know resolution of vectors can solve anything, even if there are 100 forces at different angles, I can resolve them to their x and y components, get one single x, get one single y, and get one net force or one net vector, one net resultant vector. Yes, so, and I'm going to take an example to illustrate that to you also. Let's take an example to illustrate that to you also. Hey, yes, so. Yes, so, yes, so. Hey. Now we are looking at applications of the resolution of vectors. Yes, applications of the resolution of vectors. I'm going to give you a very complicated problem, and once you know how to solve that problem, then you can solve any problem. So let's say we have 30 newtons, 40 newtons, 50 newtons, 60 newtons, 10 newtons, 20 newtons, 100 newtons, 200 newtons. So you have 30 degrees, 30 degrees, 60 degrees, 60 degrees. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 forces. 6, 6, 7, 8 forces, sorry. 8 forces acting at a point. I say find the net force. This is the kind of problem they give you when they want you to fail. But after this class, you will tell them, I came prepared. Your plan is what is going to fail, not me. I shall pass and I will get the correct result. So we'll tell you how to get one single force. So the idea is turn all these forces, first of all, to one horizontal and one vertical. Either like this or like this or like this or like this. Anyhow, one horizontal, one vertical, and then from there get one net force. Let's see how to go about that. To solve this problem, there are 3 different methods you can use to solve this problem, okay? I'm going to go through all of them. In fact, up to 4 or 5 methods depending on the level of physics, you know. I'm going to go through some methods with you. Follow the one that you are comfortable with. Use that one and you will get the answer. Yes, so you will get the correct answer. Now, when I see this problem, the first thing I do is I draw an imaginary x and y axis. X and y axis, okay? Check if there's any force on x and y axis. Of course, we have 30 this way. So I'll put 30 here. Write it here, 30 newtons. We have 40 newtons going up. I'll put 40 newtons here. We have 50 going this way. So I put 50 newtons here. We have 60 going down, 60. So I put, if there is no force, just leave it blank. The part that don't have any force. But first of all, draw your imaginary x and y. Now we come to the forces that are in between the axes, those that have an x and y component. The first one is 10. The x component is 10 cosine 30. So 10 cosine 30 will add to 30 here. And the y component is 10 sine 30 to add to 40. Okay? 10 sine 30 is the y component. 10 cosine 30 is the x component. And that force has disappeared. I cannot write it here anymore because I've gotten the x and y component. You see? You see? I go to 20. X component of 20 is 20 cosine 60. That will add to the 50 here. Y component is 20 sine 60. That will add to all that were here before. Then 20 is thrown away. I don't need it here anymore because I've gotten the components, the effectiveness. 100 Newton, 100 cosine 60 will add to what was here before. And 100 sine 60 will add to what was here before. I throw 100 away. 200 cosine 30 is the x component. It will add to 30 or whatever was there before. 200 cos 30 degrees. And 200 sine 30 degrees will be the y component. It will go down. So be mindful of the arrow. The arrow going down comes down. X, y. Those going up, y will be up. Left, x. Those here, y will be up. X, right. You know, be mindful of that. There's another method that will take care of some negative signs. We'll get the same answer. I will teach you all the method, all the secrets today. Oh, yes. Now. All this complicated diagram has come to what we know. I just sum all of this. Okay? This will give me 40 plus 10 sine 30 is 5 plus 20 is 17.32. Okay? And then this will give me 57.32 plus 5, okay? 57, 58, 59, 61, 62.32 newtons going up. That's this, okay? Then here is 50 plus 20 cos 60 is 10, 100 cos 60 is 50. So this just give me 110 newtons going this way. So this, the single force going up, the single force going left. 60 plus 100 sine 60 is 60 plus 86.6 plus 173.2. So that will give me 173 plus 30. That will give me 233.2. Okay? 233.2 plus 86. Okay? Plus 86.6. This is 8. This is 9. 11. 319.8. So this is 319.8. Going down. So this whole force reduces to all of this. It's just this. 62.32, 110. I might make some mistake from the algebra. Please verify that. And then, I didn't do this part. 30 plus 10 cos 60 is 8.6, 8.7. 200 cos is 173.2. 200 cos 30. So it's 38.7. 173.2 So 173.2, 38.7. So this is 9. This is 1. 10, 11, 1. 211.9. So this is 211.9 newtons going to the right. So 211.9 newtons. Single forces. This is 319.8 newtons. You see? Single forces. And I know when I have single forces, I know what to do. I subtract the small one from the large one, the small one from the large one. Then I get the only 2 forces I need. The problem is solved. I get the only 2 forces I need. So 211.9 is going this way. Okay, let me see. Yeah, that's correct. Okay. 211.9 is going that way. So I'm going to have 211.9 minus 110. That'll give us 101.9. So I have 101.9 going to the right. And then 319.8 minus 62.32, because this one is the larger one. So to minus this one, 62.32, the smaller one. And what does that give you when you check that? What does it give you? 184.3, okay? 184.3 newtons. Yes! My problem is done. So I'll make this bigger because I want to find the net force now, which you already know how to find. So I'll come this way. Is everything clear? Are we getting this? Are we getting this gradually? Yes. Okay. So this gives us so we have 2 forces like this and like that. So this one was 319.8 newtons, and this one was 184.3 newtons, and this one was 101.9 newtons. So I'm looking for the net force. So I complete this, remember, 184.3. I complete this to look like a parallelogram, 90 degrees this time, so it's Pythagoras. I call this R. So I say R square is 101.9 square plus 184.3 square. Okay? So when I do that, what does that give you? Let's just be fast to finish about this. What does it give you? 44350.1, 44350.1. So R is the square root of that. Okay? Okay? And when you take the square root of that, please do that for me. And what do you get? 210.6. 210.6 newtons. So just approximately 211 newtons. So that's the net force. So you can get the angle as you like. So you can get this angle theta, okay? Or you can get the other angle theta, anyone you like. So you say tan theta is opposite 184.3 over adjacent 101.9, okay? And then you do the tan inverse of that, and you're going to get, this is 1.81. So tan inverse of 1.81, that's your theta. And what was that give you again? Tan inverse of 1.81? Okay, 61.1 degrees. Okay, we've gotten our direction, 61.1 degrees. That will be south of east, or to the, you see now you can't say to the positive x-axis, because this is not the angle to the positive x-axis. The angle to the positive x-axis is this one. We always go counterclockwise from the axis to the place, so be careful. So it is going to be 360 minus 61.1 degrees. That will be the angle to the positive x-axis. So the only thing you can do with theta is going to be south of east. That's all, nothing else. Okay? Or you want to use the vertical angle to the negative y-axis. That will be correct, negative y-axis. Okay? Okay? So be careful. So you can choose whatever direction you want to get that. So the most important thing is how to get one force from that crazy combination of forces. Now I'm going to teach you another method to solve that problem. Another method to solve that problem. I'll do it right here. Then I'll do it a third method. So whichever one you are comfortable with, use it. You'll get the same result. Okay? The answers will be the same. Okay. So in this method, I want to use the second method. We draw a table. We draw a table like this. Okay. Here, we say forces. Here we say horizontal components. Here we say vertical components. So we start from the first one, we write all of them out, 30 newtons, 10 newtons, we go like that, 40 newtons, 20 newtons, 50 newtons, 100 newtons, 60 newtons, 200 newtons. 1, 2, 3, 4, 5, 6, 7, 8, yes. And here we draw a line and we say total. This is another method, another approach to this, okay? Okay, please, I will need this because I'm working from this diagram here, okay? So I want to picture this together. So 30 newtons, when I'm using the table method, I measure all my angles to the positive x-axis, this axis. All angles are coming here, all angles, counterclockwise to the force. So I start with 30, it's along the same axis, so it's going to be 30 cos 0 for the horizontal component of that, which is 30 newtons. The next one is 10. The angle between 10 and this positive axis is 30. So 10 cos 30 degrees, that will give me 8.7 newtons. The next one is 40. The angle between 40 and this axis is 90 degrees. So it's going to be 40 cos 90 degrees. Cos 90 is 0, that gives me 0 newtons. 20. I'm not using this. I'm taking to the positive x-axis. All the angles from here. So it's going to be 180 minus 60, 120 degrees. So it's 20 cosine 120 degrees. That'll give me minus 10 newtons. 50. The angle between 50 and that axis is 180. 180 degrees. I'm always going there. Once I'm using the table, I'm going there. So it's going to be 50 cosine 180 degrees. That'll give me minus 50 newtons. 100. 180 plus 60. 240. 100 cosine 240 degrees. That'll give me minus 50 newtons. 60. From here is 270. 60 cosine 270 degrees. That'll give me 0 newtons. 200. All the way back to the positive x-axis. 360 minus 30. 330. 200 cosine 330 degrees. That'll give me minus, no, it's a plus 173.2 newtons. Yes, so you see, once I'm taking the angles to the positive x-axis, all of them, I use cosine for all the x. Cosine, 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 cosine for all my x. Now, how do I get my y's? I don't need to look at the diagram anymore. For me, I just change all the cosines to sines. 30 sine 0, 0 newtons. 10 sine 30 degrees, 5 newtons. 40 sine 90 degrees, sine 90 is 1, 40 newtons. 20 cos sine 1, 20 degrees, 0.866, 17.32 newtons. 50, I change the cosine here to sine. Sine 180 degrees, which is 0, 0 newtons. 100 sine 240 degrees, that'll give me 86.6 newtons, okay? Negative 86.6 newtons, okay? And then 60 sine 270 degrees is minus 1, so minus 60 newtons. And 200 sine 330 degrees, that'll give me minus 173, what is it, minus 100, because it's minus 0.5, minus 100 newtons. Yes, I change all the cosine to sine, I get math. Then I sum all these up. Minus 50, minus 10, minus 60, minus 110, plus 173.2, I sum everything up, I will get exactly what I got here before. 101.9. That's my total x. What's my total y? I sum all these up, okay? Minus 100, minus 60, minus 86.6, I will get minus 184.3. So it is the minus sign here that tells you that the total y, the total x is positive, so it will go this direction. Your total y is negative, so it will go like this. If it was positive, it will go up, and the x go like this. If y was positive. If x was negative and y was positive, it will go like this. X negative, y positive. But here, y is negative, it will go down. So the minus just tells you it goes down. X is positive, it goes to positive. That is why we had this. That is why we had this. X positive, y negative. And then you continue from here and you just get your answer. So the table will still give you this. So the aim is to resolve all the forces into two perpendicular forces. No matter how much they are, then from there you can get one single net force. Okay? Okay, then from here you continue from there you get. So I'll teach you another fast way, another quick way for this. I'll try to do it here. It's very easy. The third method you can use just a sum of the x forces. You said 30, you know this is 30. So you just sum and say 30 cos 0 plus 10 cos 30 plus 200 cos 30. So I'm getting all the x component. 20 cos 60 is in the negative direction, so I'll say minus 20 cos 60. Or I will say plus 20 cos, I will now use the angle this way, 120. Then it will not bring a minus there automatically. So be careful, okay? So let's just use that. Let's assume we already know it's minus, okay? Then minus, because it's going in the direction 100 cos 60 minus 50, because 50 is along there. Then I'm done. I'm done with all the x components. When I sum all this up, I will get the 101.9. Then I talk about my summation of y forces. So I start with the y force 40 plus 10 sine 30 plus 20 sine 60 minus 60, because 60 is going down, and then minus 100 sine 60, this one here, minus 200 sine 30, this one here. When I sum all this up, I will get minus 184.3, and then I go back there. So I can do it on a straight line, I can do it on a table. Be careful with your angles. And then using the angle here, then you have to introduce the minus sign yourself. And this one is plus. But if you're using the angle to the positive x-axis, you don't need to put a minus sign again. The minus will come from the trigonometric value or ratio of the cosine or sine of those angles. That is the trick about this, okay? And then you get back that result. There's another method, but we won't talk that method yet because we're going to do vector geometry. See how vector geometry works. So it is by understanding vector geometry that will give us another method to solve even that problem of parallelogram law. You can decide to use the decomposition of vectors. You can decide to use the position vector method or the IJK method, which is what we want to go in now, the vector geometry. Yes, the vector geometry. Let's look at the vector geometry. Vector geometry. Zini, zini, meha. Okay. Now I'm going to wipe off the whole board. Okay, now we will not do all vector geometry. We'll just do introduction to vector geometry. The mathematicians do lots of this and prove a lot of things, but we just need to make some sense of physics from this a little bit. Vector geometry. So recall we said vectors are represented by arrowheads. So in 3 dimensions, actually, the arrows we have like something like this, okay, around that, and then they will have like a tail that has like a square. So when you look at the back of a vector, it's like a cross. When you look at the head of a vector, it's like a dot. So this is how you tell the end vector from the tail vector. So this means the vector is pointing out of the board. This means the vector is pointing inside the board, okay? And then, the way we add vectors in vector geometry is, we can put vectors anywhere as what we call free vectors. A free vector, this is a free vector. I call this vector B, this is a free vector. I call this vector A. This other free vector, I call it vector C. But I can say what is A plus B plus C. So we now use the vector notation. Now we're gonna put arrow in the symbol to show it's vector. So what is A plus B plus C? I want to sum them. So we are summing vectors like this. We put the head to the tail. A first, which is like this. B is slightly like this. So I'll take it the way it is and put it here. Okay, slightly like this. This is B, this is A. So A plus B is the head of A touching the tail of B. Plus C means the tail of C touching the head of B. Then this line from the origin of A that I started, okay, draw it towards the last vector. This line I call OP. So this vector OP is vector A plus vector B plus vector C. Okay? Okay? So if I say only vector A plus vector B, then I get one single line. I can call it vector F. So vector F is vector A plus vector B. So the net force always starts from the tail of the beginning to the head of the last, so long as you arrange them head to tail, okay? If we use symbols, it's more like that. If I say this vector OA, and this vector, say, AB, and this vector, say, BC. So I'll say, what is OA plus AB plus BC, okay? Okay? So you see, OA, AB, so OA will touch AB, this OA, and AB, and then BC. So this vector OC, vector OC coming from O to C, starts from the origin of this to the head of that. Oh, if I have 10 vectors, O, B, A, B, A, C, A, C, I'll write all of them, then the last one will come like that. Okay? And if I have the last vector, maybe it's like this, like that, like that, like that, and like that, I say, what is the sum of these vectors? It becomes 0. Because the net of this 1, 2, 3, 4 is supposed to go from here there, but that is cancelled by this one. It's like the negative of that. So I can say if A is going like this and B is going like that, find A minus B. I can subtract. A minus B is not the net vector. Net vector is the plus one. A minus B could be a relative velocity. Okay, we are going to come into those to see how it works. So it's going to be A is going this way, B is going this way, minus B is going in the opposite direction of B. So this is A, this is minus B. So A minus B is A plus minus B. So it should not be from here like this. So let me call it vector C. So I say vector C is A minus B. I can call it whatever name I want, okay? So it goes from here there. It's always from here to there. Why am I saying this? Remember when we did perpendicular vectors? They were not arranged like this. One was going this way, and we said the net vector was this. You will see it is correct. If this vector A, which we said was 4, and this vector B, which you said was 3, when we complete the parallelogram or the rectangle, you see this vector A is still like this. So it's like vector B plus vector A, which is this. So it follows this vector geometry. Or if you like, vector A plus vector B. Vector A plus vector B, it is still the same. You see that now? It is this line going from here. So it obeys the vector geometry. So sometimes when you want to use a triangle, so you have 3 Newton force and 4 Newton force, so what's the net force? You can take the 3 Newton force, take the tail of the 4 Newton, translate it as a free vector. You can move it anyhow. Put the 4 Newton force here. Then in that case, you can just draw a line here and say that's your resultant. This is correct. Because you have understood the vector geometry of how to do it. So it's tail to head, tail to head. Some people call this triangular law, but it's very useful in equilibrium. Will come there, okay? So you can see how vectors can go in different directions if you understand how to put the tail to head, and tail to head thing, okay? And how to do A minus B and A plus B. Now I want to introduce what we call the position vectors, which is very important. This is one of the methods to solve our problem. So the position vector is a vector that represents the position of a point in space with respect to some origin. This is very important in solving problems, for example. So what we do is, there's a point here. I want to know what that point is. I draw some origin O. Okay, I call this vector OA. Okay, so vector OA will have in the two-dimensional Cartesian coordinate some x and y component. So I call a unit vector here I. Unit vector means one magnitude. A unit vector along the y I call J. I hat, J hat. So say this is 5 units here and this is 3 units here. So I will say A is 0.5, 3, the coordinates. So in vector notation, the position vector OA, the vector that shows the position of that point, is 5i plus 3j. If I represent a vector like this, I don't need magnitude and direction. The magnitude and direction I already specified here. Because from 5i and 3j, I can reconstruct the vector on the ij axis, which is my I is now x, my j is y. So it's 5 along the I and 3 along the y. So I can draw that vector, magnitude and direction. So I don't need to find theta. So when I represent vectors like this, I don't need to find theta at all. This has magnitude and direction. It's a very beautiful notation. I will tell you the advantage of that. You will see what I'm trying to say right now. Now, if I say, let us represent, say this is the coordinate. I have a vector here. So say it is minus 20 here, and minus 25 here. So what is this vector B? So vector B is a position vector. I can use 2 points to represent. I can use one letter, it doesn't matter. So vector B is minus 20I minus 20J. I have represented it in magnitude and direction. Minus 20I minus 20J. Now, how can I go back to my magnitude and direction here? Very simple. The magnitude, which is the modulus of B, is represented like this. It's just the square root of the square of each. 20 square plus 20 square. You can put the minus there, it doesn't matter, but the square will be positive. Okay? So you can say minus 20 square plus minus 20 square. Minus 25 is the J, sorry. Minus 25 square. Okay? And take the square root. It will give you a number, that is the magnitude of this line. Then if you want to get the direction, you can easily get your theta because you know your x, your y. You can use your tan. Okay, you say tan theta is the x 20 over y 25. So don't use the minus. Just use the numbers and then you will get, because you can draw the geometrical part. So if you want to get an angle from a position vector, it is better you draw out the position vector, because if you use minus minus, sometimes your calculator will tell you it's an error or you can't get the answer. So draw the vector first and then get the angle from the normal way, so you don't need to use the minus. Just get the magnitude opposite over adjacent and you get your answer. Okay, it's opposite over adjacent, so it's 25 over 20. And then you get your answer without putting minus there. Okay, so you can go from here, there, and from there, there. And once you have your I, J, K vectors, it is easy. Let me tell you the advantage. So if I give you 3 vectors, in terms of position vectors, I say I have vector A, which is 2I plus 3J. I can put in 3 dimensions minus 2K. Okay? And I have vector B, I plus J minus I minus J plus 6K. And I have vector C, which is 2I minus K. So say it doesn't have a J component. Okay? I say find A plus B minus C. Okay, A plus B minus C. I just add this to be 2I plus 3J minus 2K. That's A. Okay? Plus B, I minus J plus 6K. Minus C minus 2I minus K. Simple. I take all the I's to I. 2I plus I, 3I minus 2I, I. 3J minus J, 2J. No J there, so it's just plus 2J. Minus 2K plus 6K, 4K minus K plus 3K. So this is A plus B minus C. So I say find magnitude of A. Magnitude of A is just the square root of the component. 2 squared plus 3 squared plus 2 squared. Forget about the minus signs. So that means square root of 4 plus 9. And I'll just get the magnitude. Okay? Okay? The direction here is going to be difficult because you're going to get a direction for X, direction for Y. So we'll always have theta and phi, okay, to get that. So, but just know the direction is inherent in that vector. So if I give you these 3 vectors, I say find the net vector. The magnitude and direction of the net vector. All I need to get for the net vector is the summation of the 3. My net vector, if they are F net, if they are forces, for example, these are Newtons, say they are forces. They could be displacement, they could be any vector. So the F net will be the summation of all of them. So I just turn this to a plus for the F net. So now I'm looking for A plus B plus C. Simple. So it's just going to be 2 plus 1 plus 2, which is 5. Okay? And then 3 minus 1, which is still 2. Minus 2 plus 6, 4 minus 1, plus 1 now. Okay? Okay? 4 plus 1, 5. Simple. So this is 2 plus 1 plus 2, 5i plus 2j plus 5k. I don't need to find a magnitude and direction. This is my net force. So F net is A plus B plus C, and I just added those to give me 5i plus 2j plus 5k. That's easy like that. The magnitude and direction, this is the answer. That is the answer. Just this alone. I don't need to do anything else. Okay? I don't need to do anything else. So they say find the magnitude of the net force. So F net magnitude is square root of 5 squared plus 2 squared plus 5 squared. I get a number. Okay? In 2 dimensions, it is easier to find the direction than 3 dimensions. Okay? Okay, I don't want to go into those details now. Now we're going to end with the vector geometry of multiplication of vectors. Okay? So we have vector multiplication. The first one is called the dot product. So I say A dot B is magnitude of A, magnitude of B, cos theta, where theta is the angle between A and B. It's a scalar product called dot product or scalar product. So you're going to get a scalar. So the answer is not a vector. So if I use that, I get magnitude of A. Say I get dot product of A dot B using that same numbers. So it's magnitude of A square root of 2 square plus 3 square plus 2 square. Magnitude of B is 1 square plus 1 square plus 6 square. Okay. Then cos theta. I already got my A dot B by multiplying each. So I'm going to do this in details. Okay. Let me tell you. I can get the theta, the angle between this A and B from this dot product formula. So A dot B just means 2i plus 3j minus 2k, that's A. Dot B, I minus j plus 6k. I times I, 2 times 2, 2 times 1, 2, the I goes away because I dot I is 1 and I dot anything else is 0. 3 times minus 1 minus 3 minus 2 times 6 minus 12. So it becomes 2 minus 3 minus 1 minus 12 minus 13. So A dot B is minus 13. So I put the minus 13 in the left hand side of A dot B. And the magnitude of A, magnitude of B is this number. Cos theta becomes the only thing I don't know. So I divide by whatever I get here, divide by that, whatever I get here. Let me call it capital Y, all this. So cos theta is this, I get the cos inverse, I can get the angle. Okay? You can do that from dot product. Then we have another product we call the vector product or cross product. Okay, I'm rushing this. Don't worry, when you watch the video, try to slow it down. I'm trying to cover a lot in one. Okay, I've explained the basic. So we have what we call the cross product. So this is a vector. So if I say A cross B, so this is A, this is B. A cross B is going in this direction. A cross B is going like this. So like a screw, when I go like this, I unscrew. So the direction is going to be outside the board. But if I say B cross A is this. Cross A is screwing in, so the direction is going to be the vector direction will be going inside the board. So it's always in the direction of the screwing or unscrewing. So we have a formula that A cross B is magnitude of A, magnitude of B, sine theta. So we know how to do the dot. We multiply each component I, j, k, k, and get a single number. But for the cross, it's different. So if I say what is A cross B, I have to draw I, j, k. I always put minus here to remember something so it's easier. So I take A is 2i plus 3j minus 2k. So the I is 2, the j is 3, and the k is minus 2. B has I minus j plus 6k. I is 1, j is minus 1, k is 6. So I do a cross product. I cover the I, so I say 6 times 3 minus 2 times minus 1. Minus 2 times minus 1. So this minus that is my I component. So this is still the A cross B. Then for the J component, I close the J and I put a minus sign. That's why that minus sign is there to remind me that for the J I have a minus sign. 2 times 6 minus 2 times 1. That is my J. And then the K component will be, I cover the K, 2 times minus 1. Minus 3 times 1. So it's always this minus that, this minus that, this minus that. This is my K component. So a vector product gives me a vector. So 6 times 3, 18, minus 2 times minus 1 is 2, 18 minus 2, 14i, 2 times 6, 12, 12 plus 2, 14j, but there's a minus outside here, so it's minus 14j. And then the k part is 2 times minus 1 is minus 2, minus 2 minus 3 minus 5k. So this becomes the dot product, the cross product. And what direction is this? A direction A cross B. So if this is theta, A cross B is in a direction coming out because I'm unscrewing when I go A cross B, coming out of the board. That's how you know the direction of that. So the cross product is a vector, the dot product is a scalar. So how can you use this position vector? Let's go back to that problem. Remember the problem we did for the parallelogram law? The parallelogram law problem, if you remember, where we had 10 meters and 5 meters. So All I need to do is get the x and y component of the 5. So I call this vector A, I call this vector B. So vector A is 10i because it's just along the x-axis, no j. Vector B is 5, here was 60 degrees, 5 cos 60i plus 5 sine 60j. You see that? I've written it in terms of position vector. So this will give me 4.33i, sorry, 2.5i plus 4.33j. So what is the net force? The net force is A plus B. I don't need to do anything else. The net force is just 10i plus 2.5i, 12.5i plus 4.33j because there is no j here. This is the net force. It has the magnitude direction. I can leave this as my answer. I will get my full score. 12.5i plus 4.33j. Simple. Then from here, I can go back to get that notation of before. So it means 12.5 along the x, 4.33 along the y. Okay? And then I can now get the magnitude of A plus B, my net force, or net displacement, as square root of 12.5 squared plus 4.33 squared. That will give me the same 13.2 meters that I got before. And to get the direction, I can do my sine and tan. But if I leave the answer like this, instead of going back to what I know, it is considered a correct answer. It has the magnitude and direction all inside of it. So we'll do problems next time. I'll give you more examples, even practical examples, like a man crossing a river. Okay, trying to cross a river. He has a speed in still water, and he's on his boat, and the river is flowing due east or west at some speed. So you see, these are practical examples, word problems that you want to use vectors. Relative velocities are also word problems. We want to solve the problem section. It will give us more enlightenment to have a problem section for each chapter. Okay, we solve problems to understand more. So I'm going to stop here for now, and then I'll see you next class. Thank you so much for being patient with me.